Now, electron mobility and its relation with the electric current. For lower electric field, E and Vd is the drift velocity. For lower electric field, Vd is proportional to the electric field, or the drift velocity is proportional to the electric field. Therefore, we can write Vd is equal to a constant mu into E. This constant term mu is called the mobility of the charge carrier. Here for the electrons. Now mu is equal to Vd by E. Since we have already derived the equation of the drift velocity, Vd is equal to minus half E, the electronic charge, into the electric field by m star, that is the effective mass of electron, into tau, where tau is the relaxation time. Now neglecting this negative sign, we can write half E into E by m star into tau into 1 by E. This two capital E term can be cancelled out, and we can write E into tau by 2 m star. This is the relation or the equation of the mobility, or the relation between mobility and relaxation time of the electron. Now, current density. Actually, current flowing perpendicular to unit area of a conductor is called the current density of that conductor at that point. Therefore, we can write J, the current density, is equal to I, the current, by A, the cross-sectional area of the conductor. Now we know the current I is equal to NE Vd into A, where N is the number of electrons per unit volume, E is the electronic charge, Vd is the drift velocity of electron, A is the cross-sectional area. Therefore, from these two equations, we can write J is equal to NE Vd. Look at this relation. J, actually the vector quantity. J is a vector quantity, and Vd, we know it is also a vector quantity. And this is the relation between the current density and the drift velocity. Now we know the current I is equal to N E Vd into A, and Vd, the drift velocity, is equal to mu into E, where mu is the mobility, E is the electric field. from these two relations we can write the current I is equal to N E mu into E. We have replaced Vd by mu into E into A. Therefore, the current density J is equal to I by A is equal to N E mu into E. This term in the bracket is called the conductivity of the material, and we denote sigma is equal to Ne mu conductivity of the metal or material. Therefore, J is equal to sigma into E. Here J is the vector quantity, E also vector quantity. Actually, this relation expresses the Ohm's law. Ohm's law. The current flowing through the conductor is directly proportional to the voltage applied across the conductor, provided the temperature and other physical properties remain unchanged. Suppose this is a conducting wire. The first terminal is named as A and the second terminal B. The potential of terminal A is VA and the potential of terminal B is VB, and the current flowing through the conducting wire is I. Therefore, according to Ohm's law, the potential difference or voltage across the wire is VA minus VB. Therefore, according to Ohm's law, VA minus VB is directly proportional to the current flowing through the conducting wire. Current flowing through the conducting wire I. Therefore, VA minus VB is proportional to I. If we want to convert the proportionality into equality, then we have to bring a constant term here. So this will be VA minus VB is equal to R into I, where R is the proportionality constant named as resistance of the conducting wire. Now, if we simplify this equation, R is equal to VA minus VB by I. Therefore, this is the equation of resistance of the conductor or the conducting wire, and this is the basic equation derived from Ohm's law, or the basic equation of Ohm's law. Now, what is resistance? The property for which a conductor opposes the flow of current through it is called the resistance of the wire or the conductor. Therefore, the definition or the basic definition of resistance is the ratio of the voltage across the conductor and the current through the conductor is termed as the resistance of the conductor. From the previous equation we can write R is equal to VA minus VB by I. Therefore the ratio of the potential difference or the voltage across the conductor by the current through the conductor is termed as the resistance of the conductor. Unit of resistance. In SI units, the unit of resistance is ohms. Therefore, 1 ohm, what is 1 ohm? Ohm is denoted by the symbol like this. Actually, this is capital omega. This is the basic symbol of ohm. Now, what is 1 ohm? 1 ohm is equal to actually 1 volt by 1 ampere. Now, what is it signifies? If we consider a conducting wire, if the voltage across the wire VA minus VB is equal to 1 volt, and for this condition the current through the conductor I is equal to 1 ampere, then the resistance of this conducting wire will be 1 ohm. Now, another form of resistance. Let us consider a conducting wire. Of cross-sectional area A and length L. The resistance of this conducting wire always directly proportional to the length of the wire and inversely proportional to the cross-sectional area of the wire. The cross-sectional area of the wire. Therefore, from these two relations we can write R is proportional to L by A. Therefore, R is equal to a constant term rho into L by A, where rho is the resistivity of the material of the wire, where rho is the resistivity of the material of the wire. Another part, conductance. The inverse of resistance is said to be the conductance. We denote conductance by capital K is equal to 1 by R. That is, K is equal to 1 by R is said to be the conductance of the conductor. What is the unit of conductance? Is in spelling MHO, mho, or in notation we can write this in this form, just inverted omega. Therefore 1 mho is equal to 1 ampere by 1 volt. Now series combination of resistances. Suppose there are 3 resistances resistors of resistance, say R1. This is this resistor have resistance R2. This resistor have resistance R3. The potential difference, the potential of the terminal A is VA, the terminal B is VB, terminal C is VC, and terminal D is VT. The current through all the resistances are same, that is I. Here the current through all the resistances in series combination is same, but the potential difference may be different. Here the potential difference of R1 is VA minus VB, R2 is VB minus VC, R3 is VC minus VD. So in series combination the potential difference may be different for every resistances, but the current of each resistance is same. Therefore for the first one we can write VA minus VB is equal to R1 into I. The second, VB minus VC is equal to R2 into I. Similarly, VC minus VT is equal to R3 into I. This is equation number 1, this is 2, this is 3. Now adding the 3 equations we can write VB can be cancelled out, VC cancelled out, only VA minus VT is equal to R1 plus R2 plus R3 and I common. Now if we draw the equivalent resistance of these 3 resistances in series combination, we can draw like this. Say this is R, the equivalent resistance of these 3 resistances, and this terminal is terminal A and the N terminal is terminal D. The potential is VA and this is VD, and the current through the resistance is I. Therefore for this case we can write VA minus VD is equal to R into I. Suppose this is equation number 4 and this is equation number 5. Now comparing equation number 4 and 5, we can write Ri is equal to R1 plus R2 plus R3 into I. Therefore R is equal to R1 plus R2 plus R3. This is the equation of the equivalent resistance in series combination. Consider 3 resistors R1, R2 and R3. These resistors are in parallel combination. This is terminal A, this is terminal B. The potential of terminal A is VA, terminal B is VB. Here the current will be branched in the three branches. The current in R1 is I1, current in R2 is I2, current in R3 is I3. Therefore, for this case, we can write VA minus VB is equal to R1 into I1. Similarly, VA minus VB is equal to R2 into I2. In a similar manner, we can write VA minus VB is equal to R3 into I3. Now, from the first one, we can write I1 is equal to VA minus VB by R1. Similarly, for the second one, we can write I2 is equal to VA minus VB by R2. Similarly, we can write I3 is equal to VA minus VB by R3. Here, the current is branched into three parts. So, we can write I is equal to I1 plus I2 plus I3. Therefore, for this case, we can write I1 is equal to VA minus VB by R1 plus VA minus VB by R2 plus VA minus VB by R3. VA minus VB common, 1 by R1 plus 1 by R2 plus 1 by R3. Now, if we draw the equivalent circuit diagram of this circuit, this will be like this. This is terminal A, this is terminal B, here VA, here VB, the resistance is R, current flowing through the resistance is I. Therefore, VA minus VB is equal to RI, or I is equal to VA minus VB by R. Now, comparing this equation and this equation, we can write VA minus VB by R is equal to VA minus VB common, 1 by R1 plus 1 by R2 plus 1 by R3, or VA minus VB, both sides will be cancelled out. Therefore, 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3.